Test. Good morning. Let's get started. Okay, so just a very quick review on what we did in the previous lecture. It's about impulse function. The impulse function is defined as delta t There's delta t0 when t is not 0, but it's infinite at t equal to 0. Not only that, if we integrate anywhere with a limit that includes the 0, t equal to 0 point, then the area underneath this impulse function is, sorry, not 0, is 1. So this, both of them constitute as a definition for the impulse function. So sometimes we call this impulse function as a unit impulse function because its area underneath the impulse function is 1. And we also have talked about an important property called sampling property. Sometimes we also call it shifting property. And the property basically says if you integrate the multiplication of any function with the impulse function, then the result is f of 0. So if you integrate the multiplication of any function with a shifted impulse function, then you have f of capital T, the shifted value, right? That's the shifted amount of capital T. So in the previous lecture, I had a question I was asking you, basically, just to probably clarification here. So I was asking, what is this multiplication e to the power negative 2t times delta 2 minus t? So, and I basically said this is an even function, so this is equivalent to this. And then you get negative 4 delta t minus 2, right? So maybe just a little clarification on how this and this actually is the same. We can show that graphically, okay? Yeah. So let's do this. You can start with a delta t. You start with delta t, it's right here. And then I'm going to get delta negative t. Delta negative t and delta t, because delta t is even, right? It's right here because it's function. So then delta negative t no change, still here. Then the next, I'm going to shift this delta negative t to the right by 2 units. And of course, this is equivalent to delta 2 minus t. So apparently, right, you have your shifted version of the impulse function to the right. And this is exactly the same as delta t minus 2. So if you plot delta t minus 2, and you get exactly the same graph. So that essentially gives you the sense, why this delta 2 minus t is same as delta t minus 2. All right, so and then we also have reviewed the relationship between the unit step function and delta t. Unit step function, impulse function, how they are being related. So the bottom line is, it's not a very rigorous proof, but delta t basically equal to du of t over dt, or if you integrate delta t, and then you get back this unit step function u of t. That's a results that we have demonstrated. It's not a rigorous proof, but it's a result. So apparently, you can certainly expand the results a little bit, as I was showing at the end of the lecture. If we take a derivative of 2 times u of minus 1, for example. So if you take the derivative of this function, then you're supposed to get 2 times delta t minus 1. So this is sort of a natural expansion of the result. So let's continue here. Then let me show you an example, and that'll be the conclusion of the end of this impulse function. So let's take a look at a simple example here. I'm gonna give you a graphical function as illustrated using this graph. Let's call this as x of t. This function looks like this. So there, this is a function x of t. And I want you to graph and maybe also calculate what is the dx over dt. So not only graph it, let's also calculate it, okay? So basically, can we find the expression for dx over dt? And then graph that. Okay. So graphing it, there's probably 2 ways to, but I guess more systematic way is you might want to consider to find a proper expression first for the x of t. So what is the expression for x of t? And then we can consider the next taking derivative of it, right, to get the results of the derivative. So I believe you have a little bit of exercise already in the linear time invariant system. In one of the applications, which is also part of the quiz, we'll try to test you in quiz 1. You have an input, x of t, and then you're given an output, and you're being told that this is LTI system, and then you have a new input, right? And then you're being asked to see what's the output. So let's say this is probably a new input, for example, right? So then typically what you need to do, you need to find the relationship between this and the new input, the old input. So in this case, whenever you see a piecewise function, especially like boxes like this, okay, then what you need to do, right, or what jumps to your mind is, I must be able to express this x of t using unit step functions. So because they are all flat, right, and there are boxes. So essentially the question is, how do I express each one of the box, or or in this case, there are two boxes here, right? One is over here, and then there's one over here. Okay. Can we express each one of the box using unit step function, or can we express the whole function using unit step function? Any idea? Right. Let's say if I focus on the middle box here. What do you think would be a function? Would it be for this -1 to 1 box? Duration of 2, right? Unit step function. A cookie cutter concept. Okay, you're creating a cookie cutter with an edge at -1 and 1. So, sorry. Right, that's how you create a cookie cutter. One side -1, one side at 1. Then you create a cookie cutter. And we create a cookie cutter, I think in the lecture, like from 0 to 2 or to 1. Right? And this is from -1 to 1. Okay? So no difference. But this one here will give me this portion. And this portion is flipped to the negative side. So I could just probably minus a cookie cutter. So what would be the cookie cutter for this portion? So one edge is 1, another edge is a 2. So that must be a t minus 1, and then minus t minus 2. Okay, so that's overall how you could create these boxes, right, for x of t. If you're not too sure, if you have a little if you have a little bit of suspicion about the results that are here, guess what? You could just plot out each one of the unit step function. Then you either subtract or add, and you should be able to get the resulted x of t. And there you can do a little bit of simplification, because this minus can be grouped together. That is your x of t. And now you can calculate the derivative of this x of t. Derivative xt involves derivative of multiple unit step function here. So now you can make use of results as we have derived from previous lecture. When you're taking derivative u of t, you get a delta t. Now, of course, because this shifted, then you get a shifted delta t. Second one here, you get 2 times delta t minus 1, and then delta t minus 2. This is the results for your derivative u of t over t. So finally, you can plot this out for the dx over dt. So plotting it essentially means you try to find the delta t's location. The first one is -1, going above. Second one here at 1, but the coefficient here is 2. So when you draw the impulse or the arrow, you're supposed to draw it at least twice, right? Not exactly, approximately, because of your hand drawing. Twice as much as this one here. So then you can label this as, for example, you could label this as a delta t plus 1, -2 delta t minus 1, like that. The last delta is at t equal to 2. And that concludes this question. Okay, so the other way, once you get these results here, let's get back to the question and examine it a little bit more, okay, or observe it a little bit more here. As we have actually, the way we demonstrated in the previous lecture, for example, right? If I take a derivative of this function, then derivative is always 0, 0, 0. Then at this location, you got to jump. Right, so there's a jump right here to result in the infinite slope. And then becomes 0, 0 again. And then right here, you got another jump, but because there are 2 units here, so you got to jump basically 2 units of this impulse. Okay. And again, here you get another jump here. So that's exactly what we obtained based on the mathematical derivation. So even if you don't have this one here, and you don't need to do this, and you could just simply observing it, and then you plot out the derivative. Okay. Any questions on the impulse function? Okay. This is not a very friendly function. Impulse function is it's useful, as you're going to see right now. I'm going to show you another property for how to use the impulse function. But it's a pretty abstract function, though. Because for starters, right? For starters, you can't generate an actual impulse function in reality. Right? So how could you generate an impulse function with infinite magnitude at a certain location? So that you can't. But of course, you can generate an approximate function to approximate this impulse action. So the next one here I want to touch upon is a very important property. Okay? It's called, related to impulse response of LTI system. Impulse response of LTI systems. So first, I think I need to clarify. I find often in time people get confused right now is, what does impulse response mean? So this part here. So maybe more general is that, what does response mean, right, of a certain system? Okay, so if you recall, we can use an operator to represent a system, and we can give the system an input, and then you probably will get some kind of output. So that's how we illustrate a system. We illustrate a system using essentially 3 different components, and you can see here you need a function or need a certain description of the system. Now the description of the system, mostly for now, we describe a system using a straight expression, y equal to x squared, y equal to t squared, right? But you can also describe a system in some of the example in the lecture I think I have shown you, using a differential equation, which is what we're going to cover later. So basically you use a differential equation to describe a system. And you also need 2 other components for the system. Is that, what is the input, what is the output? Those things are all general, right? But of course, the only thing that's probably fixed is this box here. If you have a system dedicated, specified, then this is fixed. Okay, this is fixed. So the right side at here, And we can also call this is response of the system. So basically, response of the system, you can, this is equivalent to saying output. All right. So whenever you say what's the response of the system, you basically you can consider, okay, this you're talking about the output of the system. But output of the system, right? It's not a standalone item. Output of the system really depends on what kind of input is given to the system. So that's why when you see response of the system, usually you see response of the system to an input. That's the connection. Okay. So now, of course, I can have different input to the system. Okay. So now I'm going to make it a little more specific. I'm going to let my input to be this impulse function. So as I said, I mean, your input can be anything. You can give it as a sinusoidal signal, cosine. You can give it as an exponential signal, or you can give it a unit step. That's fine too. But now, specifically, I'm letting my input to be this impulse function. So this is your input. Then you give it to the same system. So of course, you would expect an output, or you would expect a response. Right. So now you will get a response to delta t. Okay. Let me write it in full. Response to impulse input delta t. Okay. So then let's still call this y of t here. Okay. So this time, okay, because this is a special kind of impulse input, then we are going to define the corresponding response or corresponding output to give it a new name. So we call this response this. We call this as a new name. Let's call it h of t now. Okay. So basically, I give it a new symbol to represent the current response. Of course, the symbol is just a specific general symbol is y here, but now I'm using this. Or you could just say y of t now. Let's call it h of t. Okay. So this h of t here, right? This is called, as the title shown in here, this is called impulse response. That's how you interpret this so-called impulse response. Now you could basically say, okay, what's impulse response? Impulse response basically is the system output when the input is impulse signal. That's what impulse response is. Okay. Okay. Now, before I write down the next important theorem, okay, we can think about maybe question here is, how to obtain this impulse response? Because I'm going to show you is that this is a very important response. The impulse response, very important response. We really like to have it. Okay? And you'll see why. But of course, the question is, how do I obtain this impulse response? So there are two different ways to obtain the impulse response. Okay? First way is theoretical approach or mathematical approach. So theoretical approach, mathematical basically means is, okay, if I have the system, and of course I have the delta t, I can plug in the delta t into the system, and I can solve it mathematically. Okay, when we learn a differential equation, and we'll see how we can solve that. Right. So then you get the result. So basically, you get a h of t result equal to something. Okay. So that's theoretical approach. So you will get a very, very precise result or description or expression, whatever you want to call that, for this impulse response h of t. So that's theoretically how you can do it, right? We do that all the time, for many things theoretically. The other thing is experimentally or practical approach. Okay. Now this one would not be very accurate. So what's a practical approach? For example, let's say if I ask you, can you obtain the system response according to a sinusoidal input, right? So, and what you could do is, okay, let's bring a signal generator and then set the signal generator to be a sinusoidal at a certain frequency, at a certain amplitude. And then the signal generator will output that signal. Then we connect the signal to the system, okay, whatever the system is. Then you observe the system output using another set of equipment, oscilloscope or data collection equipment, and you plot it out. And then you can tell people, look, here is the system output according to the sinusoidal input, right? That's called experimental approach or practical approach. But this approach is only feasible if you're able to generate precisely the type of input. But the impulse signal, right? It's not feasible at all because you cannot generate, as I said, an input with an infinite magnitude, okay, at a certain location. So, but you can still maybe think of it as a approximate approach. So what could be an impulse signal? You know, when you clap your hand, right, with as quick as possible, that momentarily sound generated by clapping your hand, consider it's a very, very short duration. And you clap it really, really hard. Probably I can consider this as an impulse signal, right? And you use a hammer, you hammer the head of the nail as hard as possible. Okay, you only hammer it and then you let it go. You could also consider that as a closely to theoretically, right, to an impulse input or generating an impulse input. Right, so that's sort of the ways you can consider yourself how you can generate approximately impulse input to the system. But none of this can be ideal, right? None of this can be ideal. So that's why in the future, right, in this lecture, we will focus on this theoretical approach in terms of how to generate this impulse response based on the derived system equation using mathematical approach. Okay, so now we need to basically introduce the theorem, and then we'll see why impulse response is a very important information we would like to have for LTI system. Okay, so the theorem says for a LTI system, linear time invariant system, okay, if the system has an impulse response h of t system has impulse response h of t, and now we change the input. So now we change input to a different one other than this impulse input. Then we have the system output y of t corresponding to x of t as the following expression. So basically, here's your LTI system. And you have delta t given, you get your h of t. And now you have x of t, a new input to the system. And the same system, LTI system. The corresponding output, y of t, is given as x of t convolute h of t. Right, so that's a theorem. Okay, so let's examine this a little bit more, and then I wanted to show you a little bit of proof right here. All right, so first of all, you got to understand, right? This is all symbol here. It's a little bit abstract. When you gave the system input as delta t, it produced h of t. So it basically means, I don't know what it is, but basically assuming you know what h of t now. Maybe h of t is as simple as a sine t. And now you change the system input to a different, any different ones, okay? Any different input x of t. Then according to this theorem, right? Then technically you don't need to do anything at all. If you want to know the output corresponding to this new input, what do you need to do? You just have to convolute the current input with this impulse response h of t. So that's what this theorem is telling us here. Right, this is pretty nice. I mean, it looks like what? It looks like as long as I have the impulse response, then I don't really need to do any experiment, any other experiment at all, right? I can just convolute this h of t with the new input x of t. And here you go. Here's going to be my new output. And of course, this only applies to LTI system. Okay, yeah. For non-linear system or non-time enduring system, not going to work. But this is pretty nice, right? This is actually telling us this h of t must be a very important signal, right? This impulse signal, because the impulse response. Because somehow I could just convolute with any other input to give me this output here. Okay. So that's the point. And I also often use a good example, I don't know if it's good or not. So for example, let's say as an instructor, as a responsible instructor, and I really wanted to know how each one of you is doing, right? So, when you have 400 students, approaching each one of the students to get the response, probably impossible. However, if ideally I could get the impulse response of the whole system, then next time, whenever a student comes over here, and without maybe conducting expensive experiment, I can just plug your input and convolute with this impulse response of the whole system, which may be represented in class. Then I'll get your output. Right? So that's the idea of this impulse response here. So let me give you a very simple proof, quick proof right here. I think it is important to know a little bit, even though sometimes we don't really care about proof. So here's our system, y equal to the operator input x of t. So let's take a look at x of t. If you recall, I didn't do the review at here, but in the previous lecture, we did a review. When you convolute any time function with the impulse signal, the result is not changing. It still get back to this original time function. So this basically, right, this is results we obtained from previous lecture. Okay, so let's take a look at what does this give us. Then the input now becomes x of t convolute delta t, and I'm going to apply the formula for convolution x of tau times d delta t minus tau, and from negative infinite to positive infinite. Okay. So remember, we're dealing with LTI system here. Okay, LTI. LTI system basically says homogeneity property. When you have a constant multiplied by a function, you can take the constant out of it. Right. Okay. So if you look at the current expression in here, okay, so m convolute m the whole input at here. So technically, if you look at the function, the only thing that has a t showing up is this function here. And this function over here, right? This function over here, it doesn't really have a t. If it doesn't have a t, I can actually consider in terms of the operator, in terms of the function here. Okay, I could consider this is the c over there. Then for this particular integral here, I can move this m into this, so x of tau, then m delta t minus tau, like that, d tau. Right, so that's c here. I consider this is basically the c now. So from this step to this step, it basically means you may use a linearity property. And then from this step to the next step, and from this step to the next step, you're looking at is m bracket delta t minus tau. Okay. And what is this? This is basically meaning an input is an impulse signal. And it's a shifted impulse signal here. Right? It's a shifted. So then I can make use of this time invariant property, right? TI property. TI property says if you shift your input, then the output is correspondingly shifted. So when your input is delta t, you get your h of t, right? But this time it is shifted. You can call this is negative tau minus. So then you get h of t minus tau here, right? Shifted output or shifted impulse output. So finally, you look at the last expression at here. That is basically x of t convolute h of t. That's the formula for convolution between x of t and h of t. So this is your y of t here. So that's a proof, right? Basically, you can write your output y, okay, corresponding to the x as x convolutes h. That's a simple proof, okay? But I want you to basically remember this concept here. You know, what is system output corresponding to any other input when you have the information of impulse signal. So I'll show you an example and how we interpret this with this one here. But let me ask you first. I need to ask you a very simple question first. Okay, so for this question, for the first, this is, let's say, call it first part of the question. If I have a system and my input to the system is delta t, and output is y of t equal to e to the power negative t times u of t. What is the impulse response, h of t? This is essentially the easiest question, but I find sometimes students got stuck on this one here. They think this is a very difficult question. Input is impulse signal. Output is this. And what is the impulse response, h of t? Yes. Is it e to the negative t? That's it? Yes. Wouldn't be just y of t. If y of t, then I use u of t here, right? Multiply u of t. Yes, it is y of t here, right? Don't forget the u of t here. Because whatever I have stated as the first part of the question here, what is that? That's basically the definition of impulse response. Right? Your input is delta t, your output is this. Then whenever your input is delta t, you call the output as impulse response. So if I want you to write down the impulse response, you don't need to do any other sophisticated math derivations. Just write down the corresponding output to this delta t. Because I find, first of all, this seems to be a ridiculous question, but I need you to understand what impulse response is, right? So that's the simple checking. And second of all, you do need this impulse response to carry out the second part of the question. So then let's take a second. Any question on this? Definitely. This might basically, what is the definition of impulse response? That's what I want you to understand. Very good. Okay, so the second part of the question is, if input is changed to x of t equal to e to the power negative 2t minus 3 u of t. What is the output? Okay, so this question is very probably I'll test you in the maybe midterm. Do we have a midterm? Yes, we do, right? Yeah. So this is basically a direct application of the theorem that we just listed over here. You're given, or you're able to obtain the impulse response, and then you're giving a new input and being asked for about the new output, right? So without doing anything, then you should write down my new output should be this new input convolute the impulse response h of t. And then you can certainly write down the expression for both of the function new input and the impulse response first, and then we can think about what to do next. Your new input is giving over here, so e to the power -2, t minus 3, u of t, convolute h of t is e to the power -t, multiplied by u of t. Right, so if you write down this, if it's a 10-point question, I mean, you could already get 2 points already, right? So now the next question is, how do I calculate this convolution? And now back to the basics, right, of previous lectures to calculate the convolution using a graphical approach. But of course, in this question here, I didn't graph the inputs and output or the two functions for you. So you're going to have to be able to graph them. To graph them here, I think I mentioned in the lecture, you have to be able to graph very basic exponential decay function. You also have to be able to graph now because you're multiplying by u of t. But I think at this stage, you should have a pretty comfortable. Anything multiplied by u of t basically means what? Give you a causal signal. So you only have the right side of the function and the left side to the t equal to 0 is all 0, right? Yeah. So let's quickly go through these steps here. How can I solve this question using a graphical approach? So I'm not going to write too many steps, but here's x of t. So basically, this equal to, because both of them basically are causal signal. When you multiply u of t with any function, both of this is a causal. Right? So this is 0 to t x of tau, and then h of t minus tau d tau. So graphic approach, x of tau first. To graph x of tau, what you can do is, right, here's your function x of t. So we know it's an exponential decay function. Then what is the value at the t equal to 0? Or in this case now at the tau equal to 0. So you plug a 0 over here, so you get a -2 multiplied by -3. So it should be e to the power -6. And the rest of them can be just simply, you can just draw exponential. That doesn't have to be very accurate. As long as you draw as an exponential decay curve, right? That should be okay. And then you can plot h of plot the rest of basically plot this h of t minus tau. I guess the first thing you do is you plot h of tau first. H of tau is over here. When t equal to 0 is you add a 1. So that's another exponential decay function. So make sure it doesn't touch the horizontal axis, right? And then you plot h of the negative tau. That basically is a flipped. And then you plot h of negative tau minus t. And that's shifted to the right by amount of t. This is essentially as h of t minus tau. Right, that's it. So you got h of t minus tau, which is this one here, and you got x of the tau over here. Okay. If you want, you can plot the two graphs on top of each other. Because you're going to multiply the two graphs, right? Multiply the two graphs here. Multiply these two, and you look at the now. So this essentially now you ask the question, the two questions. How many patterns overlap do we have? For each pattern overlap, what are the t's range to give you the pattern of overlap? So in this case, there are probably only two patterns. When t is less than 0, there's no overlap. When t is greater than 0, then the overlap always happens between 0 and t. So now you could say, okay, when t is less than 0, the convolution is 0, so then the y is 0. When t is greater than 0, your convolution is 0 to t. Okay, between 0 and t, you multiply the two functions. So what are we multiplying? The first function here is e to the power negative, you change that to tau, -2, tau minus 3. Okay, and then the second function here, right, is you have to do a little bit of substitution. So what is h of a t minus tau? So let's start from the beginning here. Okay, h of a t minus tau is e to the power negative tau u of a tau. Changing t to tau, and then when you do the mirror, you change tau to negative tau. Okay. Now you see, right now I'm keeping the u at here because technically that's what the h of t is. But of course, if you're just interested in this part of the function, then right, that's e to the power negative tau. Okay. And this is e to the power of tau. So the last part here, and you're doing the shifting now, it becomes e to the power of tau minus t, and u of, technically speaking, u of negative tau minus t, you're shifting, right? Yeah. So basically for this part of segment, it's e to the power of tau minus t. This part. Okay, so then the integral here will be just multiplication of this function with this function. So e to the power -2 tau minus 3 times e to the power tau minus t d tau. And this is a lot of exponential terms here. So you got to basically make sure which is dominant variable, right? Which one is considered as a constant. Okay, so I think what I could do is for the first term, I expanded the e to the power of a 6 times e to the power -2 tau. This one I can write it as e to the power tau times e to the power -t. So this is basically back to e to the power of a plus b equal to e to the power of a times e to the power of b. So this term and this term are considered as a constant for this integral. You can take it out of the integral here. Then you're left with just e to the power -tau. So I think you can carry out the rest of the integrals yourself. Okay. You get e to the power of 6 minus t, e to the 6 minus 2t. So do practice this part. Okay, do practice this. The reason I'm showing you practice this is because I guess a little bit of difference is right now I got the u functions, right, showing up at here. But if you don't like to write the u function, you just want to write the notation for each curve segment, like what I did here, that's fine too, right? Yeah. Okay, I'll stop right here and feel free to ask me questions. Come over.